Hey, Grant, how you doing? Hi, Naomi.
Hey, Mr. Fitzgerald.
Hey, Connor, how you doing?
Good. How about you?
Good.
Okay, I'm coming. Yes, I do you.
Yeah, Mila, I'll take a look at that question once we get going. So do you want to go over the notes today for 7-1? But before we do that, I wanted to just kind of follow up on the activity from yesterday, the Desmos thing, the Marvel slide, and just wanted to share some of the interesting approaches I saw to some of these I thought were really creative. So while other people are coming in, I'll just kind of show you these. So this is one of the verify ones, right? So they I think it was, how would you change that equation so that it would hit all the balls? And for most people, and I did this, I flipped it over and then I moved it over this way so that this part here was kind of underneath this, and it would catch them and roll them down. But here somebody moved it the other way, and it still works. So there's always more than one way to solve a problem, and this worked. It's wait. There it goes. Okay, so kind of cool, different approach to things there, and then looking at some of the challenges, right? So this was screen 18, and so again, you're trying to write some graphs. So here was one approach to it. This is David did this one, so I thought this was pretty good. Right, so used one half of one graph and the other half of another graph to do that.
You want to? I'm not sure how mine went.
And then Grant had a different approach to it here, which was also really cool. So just try to drop them right on there. So that's really neat. I was playing around with this, and I thought there was one time that I hit it that it didn't hit all the balls, but I might have, I might be mistaken. But it's not always consistent, right? So you run it one time and it works, and you run it another time and maybe it doesn't work. But I thought that was a cool approach to just cut off the graph and just drop the balls right on top of it rather than try to make the path go through that. I thought that was pretty neat. Oh, this was the one I think that I was looking at. So this one is a similar sort of approach, right? And I think it gets some of them, but not all of them. And you notice that there's some gravity and some momentum in that, right? So that when this thing rolls, and so if we think about how you could change that graph to make that go through there. We could shift it to the left by changing this number down here. We could also make it not as curved by changing this number up here. I think if you change that to a 1, it makes it a little steeper. So that might make those fall off a little bit better. If you change this number over here, you might be able to hit those. And so, but still the approach is valid. And it looks like probably need to move that back a little bit more, right? And kind of use that momentum to kind of hit those. And I got most of them, but not all of them. So anyway, it's kind of cool. This one I liked using the 2 of these graphs. So using one, you could also do this by putting a squared, right? And that gives you that funnel shape. But what I liked about that is it actually caught the balls. So they didn't actually fall through there, which I thought was kind of cool. So this was number 19. So again, trying to get, all those things to fall down in the right spot. So there's some different approaches to those. I think this one kind of a stair-step approach, right? Get them all going. Use one graph to deliver them to a different spot, and then use the other graph to actually hit them through there. So it's really clever. This one, I really like this one. I thought this was really a cool way to approach it. If you watch these balls, right, the graph is going right through the center of the ball. So if you watch what happens to them, there's one ball that goes off to the right-hand side. And I've played this, probably 20 times, and every time one ball right off to the right. And so it's kind of interesting why that happened. I never got 2 that time. So most of them go to the left, one or 2 go to the right, but it's enough to hit that. So, and then this one, right, was kind of a neat approach. They're using a rational expression here, right, a rational equation, but technically, right, when you evaluate that, that just comes out to be 0. So it's just a straight line. It's really just the x-axis. And so if you just drop those straight down, nothing happens. There's no bounce to those balls, right? So they just kind of sit there. So you need something right here to kind of bump those graphs, right? Those balls to one direction or another. So this one, this Grant, yeah. Grant, I really like this approach here. That little stair step approach, and two of them, so they kind of drop down one direction, drop down the other direction. You notice that they're going slow. They're kind of rolling uphill, but all you need is one. Right, it kind of drops down and hits. Oh, get that last one. Did it ever hit that last one, Grant?
Every time I played it, it bounced off the wall and hit the last one.
Oh, did it?
Yeah.
I've also noticed that that screen resolution seems to have some effect on it too. So if you put it in a smaller screen, they sometimes will behave a little bit differently. Oh, yeah, but it's a cool approach. And then here, this person took a similar approach, right? Delivered them over here. Didn't technically use a rational expression here, but it works nonetheless. I like how they had a vertical line here to help speed that direction change, right? So if you don't have that, you got to wait for those balls to roll off the screen, and sometimes it might time out, and so like you stick that wall right there, helps that whole process along. So, and then a similar approach on this one. So this little part of a graph right here is the thing that some of those balls hit that, and it's what shoots them off to the left. So that's a really clever addition right there. And
that on its own took me half an hour.
Say it again.
That graph on its own took me half an hour.
Oh yeah. If you don't have this second graph, like this graph goes down this way, so all those balls end up rolling off to the right. So you really need that little piece right there to knock those over to the left. So very cool. And then this person had a similar approach, but they used a graph going the other direction, and their balls just shoot right off of there. I like that little arc that kind of flies off there. That's kind of cool. And again, balls get caught. So as Cameron Smith did that, it's pretty neat. And then the last one here. So this is the last challenge slide. So this is similar to what Grant did on this little kind of stair step approach. So David, I thought this was really clever. It's beautiful, right? Really simple. It's also kind of a cool shape that it makes there where those asymptotes are kind of hitting each other. And then, there's always the easy, straightforward way, right? Where, I can hit those with a straight line. And so you make a straight line. And so it works. It's not a rational expression. There's a rational number in there, but it's not a rational expression. And we'll talk about that a little bit today. So I love these kind of exercises. I love these kind of things, just playing around with them. I spent way more time playing in those graphs yesterday than I probably should have. One of the things that I like to do on I forget which one it is. It was one of these, but like to figure out like what numbers I could change to trap those balls inside there, right? So what number could I change there? And so if I put, it's going to be a bigger number on the bottom. You put like a 6 or something like that. Will they actually go down there and hit that? And those are extremely slow motion.
You should replace tests with these. These are more fun.
What's that?
You should replace tests with these. I like these better, and I think I learned more from this than I did a test.
there's a Facebook group for teachers who use Desmos, and I've been looking at how teachers have been using this as a test environment, and it's pretty interesting. So I'm kind of with you on that. Yeah.
One thing I realized is it's like moving, like these marbles are moving like really slow, like that.
Yeah.
And it just automatically, then like after some time, we'll just go back.
Yeah. It times out,
It can be
right?
really
Yeah.
annoying. Unless they're moving at a certain speed.
Yeah. So you almost need something to kind of like get them moving, right? Then,
Oh. But wait, how do you like? Can you move around the graph, or are you just stuck?
you can move the graphs by changing this number, right?
No, just like zoom in and zoom out.
Oh, yeah, I noticed that you can't really zoom in and zoom out on those. That would be a neat thing to do. But I noticed that, and I don't know if that's,
You'll see where the marbles.
if it's just part of the marble slide thing. I think on most of the Desmos things where there's a graph, you can zoom in and zoom out. So they may have just disabled it for this activity, but anyway, I don't know. I have a ball with these things. I could just sit and play with them all day. So, and that's kind of the point, right? That's what we're trying to do. Here's somebody who solved that problem, right? Of them going too slow. Right, by just putting some line, putting 2 points in there and drawing a line in between them. Like that's pretty clever. Another way of drawing a line, right? You put 2 points in and you tell it to connect the dots in between them, right? So it's kind of a neat thing. All right, so that's that. So I've been talking about some of the other classes, just about kind of the pace that we're going and, you know, where we're going to end up and things like that. So, you know, this whole idea of doing a year-long class in a single semester has never really sat well with me. I think the pacing is too fast. And, you know, with math, it's a little bit of a tricky thing because when you get past Algebra 2, right, you get into like college level classes. And so college algebra trig, you know, you can get college credit for that. Statistics, there's an AP stats class. There's, I think some places offer, I think it's Math 112, which is trigonometry. They offer some college credit for that. Calculus is an AP calculus test that you can take and get college credit for that. The problem when you start getting into college credit, right, is that they assume that you have a certain set of skills and you've gone through a certain amount of material. So when you go into those classes, like they're assuming in college algebra, you know, that you know all about logarithms and you know all about quadratics and you know all about rational functions and you know, like they just assume that you know all that stuff and they start moving forward from there. So what we're running into this year is that, you know, by condensing those classes into a single semester, we up the pace of that. And, you know, I see more and more people kind of falling behind. And so that's my concern. I can certainly slow down the pace of the class, but the problem becomes that we don't quite cover all that material. So we don't get to, you know, logarithms and exponential functions and, you know, that sort of stuff. And so then when you move into that next class, you know, and they make that assumption that you've already got that, then you're kind of stuck. And so that's an issue with just math classes in general. But it's kind of exacerbated, you know, this year while we're doing this condensed schedule. So, and it's not just Algebra 2, right? It's all the math classes are having these same issues. So if Algebra 1 doesn't get as far as, you know, as we typically would, then we take more time at the beginning of Algebra 2 to go back and kind of relearn and and touch upon those topics. But that just means that we're farther behind then in Algebra 2 than we would be for college algebra. And so it all kind of just builds up and compounds. So anyway, my point is that like I understand the issues that you guys are going through. I understand that this is a condensed schedule, and I understand that you know, you're being asked to do a lot. I want to try to minimize that, you know, those problems as much as possible. So, you know, one of the things is, you know, your assignments aren't considered part of your grade. So, you know, if you miss an assignment, it's not really affecting your grade. It might affect your ability to do the test, right? It might affect your ability to kind of master that material, but that assignment itself is not really affecting your grade. I've put more of an emphasis on the practice tests just simply because they're more of a direct reflection of, you know, what you're going to see on that test. And so it's kind of just condensing that focus to here's what you're going to be tested on. Again, not the best way to do it, but you know, I'm trying to minimize the effect of this condensed schedule. The other things that, you know, I've done for other students, and I think I've offered this before, but I just want to make sure you guys are all aware. You know, if you start falling behind, your focus should be on those practice tests. Like that's where you should be focusing your attention, and you should be working those problems as many times as you can so that you feel confident in how to do those problems. Okay, so you have unlimited attempts in those problems. You get 2 chances per problem, and then you can ask for another question, and you can just kind of keep working those problems. There's videos embedded in those to look at those. If you're going through those and you're still finding like you're not getting it, then, you know, ask for help. Right? There's lots of ways that I can help. I'm happy to work problems in class. That's an easy way to do it. But, you know, you can email me. I've had people do that this morning. In fact, right before this class, I made a video for somebody and just like went through a problem. They said, I don't know how to do this problem. They sent me a screenshot of the problem. I made a quick, you know, 5-minute video, worked the problem for them, sent them the video. And so that's an easy thing to do. I've also gone through for some people and like provided feedback on their practice test. So, you know, they got a 70 something on their practice test and they're not quite sure what they did wrong. And so I can pull up their practice test and just go through it. And again, I can make a quick video of that. I can make a PDF of that, you know, practice test and write feedback on it. I can meet with you guys individually, one-on-one. We can do a Zoom call and we can just go through that practice test together. I've done that with a number of people. And again, I can, you know, since it's all video, like all of it can be saved, and I can send you videos of this stuff, and then you can take a look at it and kind of go through it at your own pace. But the biggest thing, right, is that if you're stuck or if you're feeling behind or if you're just feeling overwhelmed, the biggest thing is to say something about it, right? Talk to me about it, and let's figure out a way to get you some help, okay? I'm going to try to just keep moving with this stuff. I know that there are a number of people who still haven't done the Unit 6 second test on that, but I want to keep moving ahead because there are a number of people who have taken that and are ready to move ahead. So we're going to keep moving ahead, but kind of keep those help options right in your mind and with what we're doing there. So I want to spend just a couple of minutes going through the notes I have on the website. I have the blank notes there that I'm going to go through here. I haven't created a video for it yet. I was too busy playing Marble Slide, and I didn't get my video done. But I'll go through those notes here in just a second, and I'll post a video later today on that. All right. So that's what I want to do right now, and then hopefully that'll answer some of the questions that you might have about that 7-1 assignment. And then if not, then we'll have a few minutes to go through any questions you have on that as well. All right. Okay, let's take a look at that. Okay, everybody see that okay? So this unit, we're going to be talking about rational functions, right? A rational function just means anything where there's a variable in the denominator of a fraction. So that's what we were playing with yesterday, right? All those graphs that we were making, the x is always sitting down there in the denominator. And sometimes it's an x, sometimes it's an x squared, sometimes it's an x cubed. I mean, there's all kinds of things you can do, but that variable in the denominator is what makes it a rational function. They're also referred to as inverse variation, and that's what we're going to talk about today. But they kind of use those terms interchangeably. So inverse variation and rational functions, rational expressions, they're all kind of talking about the same thing. It's that variable down in the denominator of the fraction. All right, so the biggest thing, and we kind of started this yesterday, is like, what are these things, like what are they? What do they look like? What are some of their features, like some of their behaviors? How can I tell if I just look at a graph? Can I tell that it's a rational function? Are there any kind of telltale signs of that? And then this idea of this inverse variation. So we'll talk about those today, right? So before we talk about inverse variation, I want to kind of go back and talk about direct variation, okay? We've done direct variation before, even though we may not have called it that, and whatever class you had may not have talked directly about like direct variation, but direct variation just means that there's a relationship between two variables that is the product, right? So one variable represents some number times the other variable. So it's that product that we really care about. So that's a direct variation. And so if I say that y varies directly as x, what that means is that my y value is just my x value multiplied by some number. Okay, that's direct variation. I could say y varies directly as x squared, and that would just mean that my y value would be x squared times some number, right? So it just means, right, the variable of that relationship just times some number. So, so if I know that this is a direct variation, right, my y value is just my x values times some number. If I know what that number is, I can figure out everything I need to know about that equation. So that's what these are kind of looking at. So it tells me that y varies directly as x, okay? So I know that this is the relationship. That's what those words mean. And then it gives me some other information. It tells me when y is 12, x is 3. And so if I say, well, y is 12 and x is 3, then I can tell pretty easily, right, that k has got to be 4, right? That whatever my x value is, my y value is going to be 4 times that. And so if they say, well, when y is 20, right, what's my x value going to be? And so now I've got this equation, right? I know that y is equal to 4x, right? I know my k value is 4. I know that y is always going to be 4 times what my x number is. So I know if my y value is 20, my x value has got to be 5. Okay. So I'm using the fact that it's a direct variation. I'm using some of the input numbers to come up with that equation, and then I can figure out everything I need to know about that relationship. All right, so that's direct variation. These are also linear equations, right? If I were to graph this, right, this would be a linear equation. It would have a slope of 4. It would go through the origin, right? So we've talked about direct variation. Only most of the time we talk about it as linear equations.
Mr. Fitzgerald?
Yeah.
My computer just cut out like for most of it, so could you kind of go over it because like I didn't really understand.
I'll post a video of this, and so you can go back and rewatch it. Really, I was just talking about direct variation, and direct variation is just a linear equation. Okay, it's just a different way of talking about it. What we're really going to talk about, though, we're really here to talk about today is inverse variation. All right, so that's really what we're going to focus on today is this inverse variation. So inverse variation means that instead of multiplying x by some number, what I'm going to do is I'm going to take some number and I'm going to divide it by x. Okay, so when I say that this is an inverse relationship, that means that there's some number on the top and it's divided by x. Say that x is in the denominator of that. Okay, so that's what an inverse variation means. It just means that my equation has this kind of format. And so I can solve this kind of in the same way. So it tells me that y varies inversely as x. So I know that this is the relationship between x and y. And the only thing I really need to know is what is this value right here? What is this k value? So they give me some clues here. They say that when y is 6, then my x value is 30. That's a k. And so if I need to find out what k is, I'm just going to multiply both sides by 30, and I get this has got to be, k has got to be 180. So my equation is y is equal to 180 over x. Okay, so that's that inverse variation, right, for this situation. And then they ask me something else here. They say, what's the value of x when y is 14? And so now I can just plug in y is 14. And so I can say, well, y is 14. Okay, and I can solve this equation. I can multiply both sides by x. I'd have 14x is equal to 180. Divide both sides by 14, and I get x is 180 over 14, which would be, what is that, 90 over 7.
Mr. Fitzgerald?
Yeah.
For my first equation, it's y varies inversely as x. If x is 7 and y is 3, find y when x equals 4. So I'm trying to figure out the y, the first one, x is 7.
I'll go through and answer questions and work problems for you guys once I get through these. I just got a couple more slides to go through, and then I'll go back and answer those questions, okay? All right, so we talked about inverse variation. This is also called a rational equation. Right, so that rational part, right, that rational part means my variable is down in the denominator. That's what we're talking about when we talk about rational equations. Okay, so we've got a rational expression, right, again, is just any expression where the variable is located in the denominator of the fraction. So these are all examples of rational expressions. If this was y equals or f of x equals, these would be rational functions or rational equations. But the rational part means that that variable is down in the denominator. And it doesn't matter if it's an x squared or an x. Here I've got an x in the numerator, but I've also got an x in the denominator. So these are all rational expressions. Okay, I've got that variable down in the denominator. It's a rational expression. Okay, and this is kind of what we were playing with yesterday. We were looking at the graphs of these, right? How do these things work? What controls what? You know, what happens when I change A? What happens if I make A negative or positive? What happens if I change that B value? What happens if I change that x minus B to x minus B squared? What does that do to the shape of that? What if I change the C value, right? What do all those different things do? So that's what we were playing around yesterday. So these are some of the terminology that you'll see with it. So we have solutions, we have y-intercepts. Those mean exactly the same. The solution would be, you know, where it crosses the x-axis. The y-intercept would be where it crosses the y-axis. All right. But these rational expressions have these features to them. One is called a vertical asymptote. So the vertical asymptote is right here. This is the vertical asymptote. Okay, this is that split in the graph, right? This is where we were trying to make the balls roll down that, right? That number that they roll down to, that's That's the vertical asymptote. What that represents is it represents where the domain is undefined, right? It's the domain that gives us an undefined value. So in this case, it's the thing that makes x minus b equal to 0. So if I have a value for x that makes this 0, this function is going to be undefined. And that undefined spot is right where that splits. Okay, so that's called a vertical asymptote. And then there's also a horizontal asymptote. Right? This is split kind of in two directions here. So the horizontal one, right, is where this rational part right here is equal to 0. So where that rational part is equal to 0, we'll have another split right there. Okay. So when that's 0, my y value is c. So my horizontal asymptote is where y is equal to c. So this is the horizontal. Okay, so the horizontal asymptote and the vertical asymptote. Okay, those asymptotes are really the things that kind of define it. And then where those asymptotes cross, this part right here, right? This is the coordinate BC. Right, so that's right there. It's not actually a point on the graph, but it's where those asymptotes cross. It's kind of the center of that graph. Right? So BC. All right, so some of the things they'll ask you about, they'll ask about excluded values, right? Or they'll say, what's the value of x that can't be in this, okay? And they're asking really, what they're asking for is where is that vertical asymptote, right? What's the value of x that vertical asymptote is on? And it's what makes this denominator equal to 0. Right? So when that denominator is equal to 0, my function is going to be 1 divided by 0 or some number divided by 0, and I can't do that. So I would say, well, 7x plus 5, right, cannot be equal to 0 because that would give us an undefined thing. So what value of x gives us that? So I'll just go ahead and work this. Even though that's a not equal to, I'll solve it the same way. I'll subtract 5 from both sides. Divide both sides by 7. And so I know that x cannot be negative 5/7. Okay. Or another way of saying that is that this function has a vertical asymptote at x is equal to negative 5/7. So just to the right of 0 is where that graph splits. Okay. I can also tell from this that the horizontal asymptote is 0, right? Because my c value out here is 0. So if I were to look at a graph of this, right? If I had negative 5/7 was right here, and y equals 0 is the x-axis here, then I know that my graph is going to do something like this. Right? Or maybe it goes the other way. You know, maybe it goes this way and this way. So I have to understand a little bit more about it, right, in order to tell it directly, but I can get the general shape of that graph. I meant to have a +1 on this, right, but it kind of works out to be the same. The excluded values of this domain are just where x plus 1 is equal to 0. So x plus 1 can't be 0. So that means x can't be negative 1. Okay, so excluded values of there would just be negative 1. And again, I can tell that this graph has a horizontal asymptote at +1, a vertical asymptote at -1. I could calculate some other values if I wanted to. I can get a general idea of what the shape of that is just by understanding that equation. All right, and so then these are some of the questions that you guys were asking about. So these y varies inversely as x. So what this means, right, y varies inversely as x. So not x squared or anything like that, it's inversely as x. So that just means that y is equal to k over x. And we don't know what that K value is, but we need to find out what that is. And so if it says some other information here, when X is 7 and Y is 8. So 8, Y value is 8. I don't know what K is yet, but my X value is going to be 7. And so I can solve this. I know that K has got to be 56. So my actual equation here is Y equals 56 over X. So that's the equation, right? That's my K value in my inverse variation equation. And then the last thing they asked me to is they say, well, what about Y? When X is 2, what is Y equal to? So I just plug that in. 56 divided by 2. I know that Y's got to be 28. Okay. So when X is 2, Y is 28. I had a question about how do I know it's going to curve like that? So in this example right here, I didn't actually figure out any other points, but I can see, right, those asymptotes, right? I can see where those asymptotes are. And so I know there's an asymptote at -5/7, and I know there's a horizontal asymptote where X is equal to 0. And I can tell that just by looking at the equation. All right. Now, if I wanted to find out exactly where that graph went, maybe one part of it's over here and the other part's down here, and maybe it goes the opposite direction. Maybe it goes like this and like this. But I know it's going to split right along these horizontal and vertical asymptotes. Okay. So if I wanted to figure out which was which, right, I can plug in a point, and so I can plug in. Let's find a value for. So let's say when X is 0, right? What do I get? I get 1/5. So at 0, 1/5, right? There's a point right there. So I know my graph goes through that point. So I know that it's got this shape, and I know that it's. My thing just crashed. Anyway, I can tell, right, by that one point that is going through what that's going to look like. I don't know if that helps, but I know generally what the shape of that graph looks like, and I know because of those asymptotes, and then I can just look at one point and kind of figure out how that graph sits on there. Give me 1 second. I'm trying to get my notes back here. Yeah, so right here is where we were looking at. So we calculated that one point, and we said it's going to go through 0 and 1/5. And so that tells me, right, that graph is going to go through the point 0, 1/5. So 0, 1/5, the graph's going to go through that point. And I know it's split right here, and I know it's split right here. So I know that graph's going to do like this. Something like that. And my drawing's not very good, but I can tell generally that's what the graph's going to look like. Right. Horrible drawing. Okay, and so there's the Y varies inversely as X, right? So we plug in the values. We know the general form of that equation, that Y varies inversely. And then we can plug in our X and Y values, figure out what K is, that constant. And then once we have that equation, we can go and figure out any other value of X or Y. Okay, and then the last example we'll kind of look at here is, so here's another inversely, right? And what we want to do is just write this equation, right? What's this equation? And so here, instead of X and Y, they're using V and T. So V right? V varies inversely with the square of t. So we're talking t squared. So equals k over t squared. Okay, so the inverse is, it varies inversely with the square of t. And so we're going to figure out what k is, and so we'll put these values in. 10 is equal to k over 5 squared, which is k over 25. Multiply both sides by 25, I get that k is 250. So my equation is v is equal to 250 over t squared. Yeah, Candy, these inverse variation graphs, right? They always kind of look like this, and they're kind of symmetrical about a 45-degree angle here, right? So the inverse with x, right? They all kind of look like this. If it's inversely with x squared, it looks something like that. Right? And that's kind of what we were playing around with yesterday, just understanding how those graphs work, right? What do they look like? But they do have that symmetry to them, yeah. Okay, so we look at the homework assignment here. So you've got a bunch of questions, right, where they just give you, they tell you that it's some sort of relationship, and then you have to figure out, you know, what the k value is, and then, you know, find some other values. So y varies inversely as x, right? So on all these, right, where it's y varies inversely as x, it's going to be y is equal to k over x. And then you're going to plug in your values of x and y, figure out what k is, and then you can answer the rest of those questions. Okay, the same thing with number 2, y varies directly or varies inversely as x. Question 3, y varies inversely as x, right? So those are all the same way. We're all just setting up this equation, plugging in numbers, figuring out what that k value is, and then we can answer the questions. So here's a slightly different one. So this is using L and C instead, and it tells us that varies inversely with the square of L. So the square of L. So this relationship here is C varies directly with the square of L. Okay, so that's the general form. And so you plug in C and L and figure out what K is, and then you can write that equation out. On this one, right, they're just asking you to fill out that table of values. And so, you know, these are not hard to calculate. You know, 4 over -4, I know that's going to be -1. 4 over -3 is going to give me -4. Sorry, 4 over -3 is going to give me -4/3. Okay. Oh, it's telling me that's not a decimal. They want it in decimal, so I'd have to convert that to a decimal, right? So -1.33. So I can just do those. If I really don't want to do those, right, I can always put this into here. I can say f of x is equal to 4 over x, and I can turn that into a table of values, and I can just type in the numbers that I'm looking to find out. So -0.5, right, -0.25. So I can just build that table. But you see what that graph looks like. Okay. So it's got a vertical asymptote right there at 0. So where if I put 0 in for x, right, put 0 in for x, I get undefined. Right, so it's undefined right there. And then the plus c part, right, is 0. So it hasn't been, there's nothing added to it. So we got the other split there, that horizontal asymptote where x is equal to 0. Okay, so the table of values you build there. Same thing here. They just ask you to calculate some values. And then there's some story problems here. Again, these are just, you know, inverse relationships, right? It's inverse variations. So, so like for number 8, they tell us that y varies, or sorry, they tell me that the weight of an object varies inversely with the square of the distance. So I know that I'm going to use W is equal to weight, and D is equal to the distance from the center of Earth. Okay, so it tells me that. So those are the variables I'm going to use. And so when I write out that expression or that equation, it tells me that the weight of an object varies inversely with the square. So I'm talking about a square here. So I got W varies inversely with the square of the distance. Okay, so I know that that's the relationship. And then they give me some values there. They tell me that the weight is, when the weight's 80, I know they're 3,960 miles from the Earth center. And then they ask you about, you know, a different weight, right? So you're going to calculate what K is and then answer the rest of the question. Okay, so 9 and 10 are kind of the same way. They're going to tell you that it, you know, what kind of relationship it is, whether it's an inverse or inverse with the variable or inverse with variable squared. So here the volume of the gas varies inversely with the pressure of the gas. So we're going to use volume and pressure are going to be our variables. So V is going to be equal to K over P. Okay, this is volume, this is pressure, and that's our constant. And so you put in the numbers and figure out what those values are. Sometimes these numbers can get big, but don't let that scare you. Like, use a calculator to calculate those out. Loudness in decibels is also an inverse variation. So there's a problem about that. So it's a square of the distance, right? So this is the distance squared. And then the last two, they're just going to ask you, like, what are the values that X can't be, right? What's a value that's not in the domain? And again, that's going to be where this denominator is equal to 0, right? So I know that 2x plus 2 cannot be 0. And so I would solve for that. I would find out that x can't be -1. Okay, so the only value not in the domain is where x is equal to -1. And I do the same thing here. Right, 6x plus 8 can't be equal to 0. 6x plus 8 can't be equal to 0, because otherwise that'd give me undefined. And so if I solve that, I get x cannot be, what is it, -4/3. Okay, so those are kind of the big ideas. Understanding that language, rather than talk about why is inverse. Sorry about that. Y varies inversely as x. Y varies inversely as x squared. Volume varies inversely with distance squared. You know, we're understanding those inverse relationships or those rational functions. And then just understanding some of the properties of the function, right? How to evaluate them, When we look at the graphs of them, can we talk about the different values and where they represent and how those relate to the equations? I went through that kind of fast. I will go through and make a video, another video of those notes and post that later today. So if you need to go back and kind of review those, I'll have those out there. So a couple people had questions. So Mila, does that, you kind of get an idea of what you're doing there on 7.1? And Connor, you had a question about one of yours. Did you get it figured out?
Yes, I did.
Awesome.
Some of the problems have the answers where it's a decimal, and I'm like,
Yeah. And that's just the nature of the problem. Sometimes the problems, require it one way or the other. You should be able to move back and forth pretty easily between decimals and fractions. You guys know how to turn a decimal into a fraction on a calculator, on a regular calculator?
if it's 2 digits, you put it over 100. If it's 3, you put it over 1,000. If it's 1, you put it over 10.
Show you an easy way. Somebody give me a decimal. 0. Let's go 84.
34.
834. Okay. So what I want to do, right, is I want to turn that into a fraction. So I'm going to go math, fraction, enter. $417 over 500. Easy peasy, right? And again, you could do that. You could say, well, that's 834 over 1,000, and then simplify that 417 over 500. It's not totally difficult to do, but that one couldn't figure out a fraction for me. That one didn't work. Must be too big.
Mr. Fitzgerald, now you can enter 46 into the equation.
Whisper. 1.06 decibels. You see how I figured it out without even doing any calculations? Decimals is awesome. All right, guys, bell's going to ring here any second. So, again, I'll have a video up going over the notes, but take a look at the problems, take a look at the videos within the problems, and let me know if you have any questions about anything. And, you know, if you're stuck on anything else, practice test, you know, anything else like that, please let me know. All right, I'll do whatever I can to help you. Have a good day.